So let's consider the generic case. So now we have polynomials capital Fi whose differential coefficients are generic differential variables. So now the domain of the coefficients is this one. And we look at the differential elimination ideal. And the definition of the sparse differential resultant given by Li Gao and Juan is this one. If the dimension of this elimination ideal is n minus 1, then this is the saturated ideal of an irreducible differential polynomial in this differential domain, which is what they call the sparse differential resultant. So as I said, they already give in their paper, they already give order and degree bounds. The order bounds are given by these Jacobi numbers. So if we do, well, let me get into it. So what happens if we use this polynomials DL to see what are the order and degree bounds? Let's assume that the system is, this generic system is super essential, so that we have the appropriate size of the matrices to compute the determinant DL. And this DL factors, and let's call Q the irreducible factors. And this algebraic elimination ideal is a prime ideal, which has a generic zero. A generic zero that you can, I'll give you an example in a minute, so that I don't use a lot of time with that. But it's defined from very naturally from the original polynomials in this algebraic generic system. So you can take that generic zero and check which of these irreducible factors are zero when evaluated in that generic system. And that will tell you which ones are also in the algebraic elimination ideal. Then to obtain a polynomial in the differential elimination ideal, in here, then we can take one of these irreducible, each one irreducible factor, and do the specialization. And if it's non-zero, then the specialization is a polynomial in the differential elimination ideal. The question is this a multiple of the differential resultant? Well, for that we have to demand something. We don't know yet that I don't know yet that it happens always. But if this irreducible polynomial is the defining polynomial of this elimination ideal, I will say, what is this? And so, given a Q, then maybe this Q doesn't need all the polynomials in the algebraic generic system to be obtained through the elimination. But there's a subsystem with the minimum number of polynomials in the original one, whose elimination ideal contains Q. And when this is the generating polynomial of this one, then we can guarantee that the differential resultant is a factor of the evaluation. So if the specialization of the DL, so our differential resultant formula is non-zero, then we can, and if one of the irreducible factors verifies this, we can guarantee that it's a multiple of the differential resultant. Here is an example. So we have this system P. This is the extended system through derivation. This would be the algebraic generic system. And using the software binaries, we can get D1P, the determinant D1, which has these irreducible factors. and only Q6 is in the algebraic elimination ideal. We may wonder if Q3 is also there, but we take the generic zero. It's very natural here. If you take P1, take the homogeneous part minus the homogeneous part of each one of these PI's, gives you the entry for the. So we need a generic zero to replace all the algebraic indeterminates in the coefficient set. So we replace the independent terms of these polynomials by minus the homogeneous part, and the other ones remain the same. And this way we have a generic zero. So only Q6 is 0 after this substitution, and the evaluation of Q6 is different from 0. In fact, it's equal to A21 times this H0, and this is the differential resultant. So if the evaluation of an irreducible factoring of that kind is different from 0, then the order of this evaluation gives you an order bound, which is less or equal than the Jacobi number minus the gamma. In fact, we can use it also to give a degree bound. If the resultant of this subsystem associated to Q is non-trivial, then it coincides with Q and generates this algebraic elimination ideal. And the degree of the differential resultant is less or equal than the degree of this evaluation of Q. And this tau would be the order of the evaluation of Q. And because this is the algebraic resultant, then the degree can be given in terms of mixed volumes. How much time do I have? Or is it time now?
About 15 more minutes.
15? Okay. Okay, then I can say, what can we do when all the irreducible factors of the DL are, when evaluated, are all 0? Well, then we can compute from a given Q, we can obtain polynomial H in the differential elimination ideal through this algorithm, let's say. And we need under some conditions, then we can guarantee that that one is a multiple of the differential result, and that one more than that one, an irreducible factor of that. So this, let's say that the evaluation of this Q is 0. So through the algorithm we get some H, which is in the differential elimination ideals, and this H has an irreducible factor. Let's call it H0, which is here too. We can detect this factor also using a generic 0 of this prime ideal. It's also naturally defined from the original system, from the system E. And then this H0, okay, so let's say that sigma I is the order of H0 in the coefficient set of Fi. And then this H0 is in fact inside the elimination ideal when you take these Fi's up to order sigma I. Here we will have to write the evaluation of the coefficients, let's say evaluation of the coefficients, the coefficients of the polynomials. Okay, so from this one we get an algebraic generic system, and the C's appearing on the corresponding algebraic generic system. We evaluate them. And then this H0 is in this idea. Well, again, if this is a prime algebraic ideal, if it has codimension 1, H0 is irreducible, so it will be the generator. And under this condition, then H0 is actually the result. So alpha is rational. So then we can say that the H that we obtain through this specialization algorithm, if it has an irreducible factor verifying this condition, which is, I don't know yet how strong it is, so it would be interesting to see how often do we have that, or if something in the process that we are doing is forcing us for this.
Do you have an example of this case?
Well, I do not have an example. That's true. That's something I'm looking for. I do not have an example of the case where it's 0 still, but I cannot say it doesn't happen.
Yeah.
Well, in fact, maybe I do have, but yeah, there's a lot of work in this direction still. But it may be that under some conditions we cannot even have this, so then this doesn't apply. This is in the generic case. Of course, in the non-generic case, it's easier to find cases where the specialization is 0. Well, and if we assume that the Q, where this is coming from, is giving the differential, the algebraic resultant, like in that case, then you can again give degree bounds or using the mixed values. And the order bounds are given by the order of, well, of course, is equal, but the order of the result of the specialization algorithm. So then we do have an object. We have a differential resultant formula that is a multiple of the differential resultant. But of course, there will be still a lot of work to do. First, to describe this extraneous factor. It's a multiple, so who is this E? This extraneous factor, because in the algebraic case, this is the determinant of a submatrix obtained from the matrix that gives you this part. And there's more study to realize, to decide exactly who is the support of the differential resultant, because here is obtained from the algebraic case to this specialization, but what happens in between is not totally controlled. So there's more work to do to decide on what is exactly the support. And well, then hopefully could be expected that having such a tool, then we can use it to in the differential case in similar manner to which is used in the algebraic case, where many applications were obtained from similar results, but the computation times and complexities and capacity of the computers are high for computing these things, so I think a lot of work is necessary to improve those. And that's all. Thank you very much.
Questions? What are the typical orders of magnitude of these bounds?
the mixed volumes.
Right.
Right.
I mean, you give a formula, but I have no sense of how big it is or how small it is in terms of, let's say, the given system. I mean, it's not like a formula. It's not like
remember something.
It's not even an asymptotic formula.
Yeah, I don't know so much about that, but I remember from what I read. I mean, from these things, I read the necessary to be able to use them. But I think it's related with the. It's totally related with the support. So
it's only computable, but not really having a theoretical formula. I mean, a formula I can actually lay my hands on in some sense. I mean,
it's commutable.
Is it
the examples I saw,
is it still exponential or polynomial?
In the examples, they are far from the type bound. They are not so close to the type. In the examples I saw, they are not that close.
Is the bound known to be typed?
No.
Okay.
No.
So is it polynomial nature or exponential or what?
I think it's
maybe exponential. Like
only
for the algebraic case, it's like the product of the degrees of the polynomials in the worst case. Because when we have
like a Bézout bound.
it's a Bézout bound.
Like the Bézout
Yeah.
bound.
Because it's like a volume. If you think of all the same support, polynomial with same support, and all simplices, that's Bézout bound.
Nice. So this is generalizing of Bézout bound.
Yes.
Yes.
Pragmatically, what's the biggest system you can compute?
Well, I have two problems with that. The biggest.
Give an example. That's the order. That's the degree.
Yeah,
that's the
not
number
very
of,
high, not very high. I tried with two polynomials, order 1, order 2, and don't put too many segments, very few. But I think there's another problem. One, we'll have to get hands-on it because when I'm doing this through Emili's implementation. I'm sure he has one available on the web. I'm sure he has far better ones because that one is from 2004. I'm pretty sure he has very new ones and improved. I didn't. One would maybe could ask, but for some systems I get an evaluation error in the algorithm, and I think it might be something technical that depending on the system I give, because I couldn't believe that it cannot be computed through the algorithm. Probably the theoretical algorithm I'm sure is correct, but in the implementation there may be a bug or something that I cannot go further. One interesting thing is that I did try with characteristic sets to compare, and whatever example I can compute with this, using the mirrors and then the specialization, I can compute it with characteristic. This I could. The other way around was not. And there was some of them that I could compute through this, and I couldn't do through the Rosenfeld-Grabner algorithm of default, out of memory, these things. So possibly is of a better complexity, but well, there's a lot of hands-on to do on there.
When the system that you start with, are you assuming it is prime?
The system,
P.
the idea,
P, yeah, right.
the differential idea.
Yeah, do you assume it to be prime to have all this?
Is the differential
You mentioned
ideal.
a few times that was
Well,
prime.
the differential ideal, this one.
Yeah, P.
I don't have to assume it. It is prime.
It is prime.
It is prime. You can. So let's say that the FIs are some AI monomial.
Right.
And some more monomials by H. I'm just going to highlight one. One of the monomials.
Right.
Then let's define this to some of the. So it was Gauli and Juan. When they define the sparse differential resultant, the first thing they do is to prove that this is a prime differential ideal.
Okay.
Then they define, maybe I didn't mention that, then they define the resultant to be the generator of the saturated ideal. This is the saturation of an irreducible polynomial when it has codimension.
Right.
So it is prime. The thing too that is, it doesn't have to be codimension one. They did prove that codimension one is equivalent to being what they call differentially essential. Differentially essential is like the extension to the differential case of the condition for algebraic multivariate polynomial, which is algebraically essential. The algebraically essential is equivalent with the existence of non-trivial algebraic resultant in the differential case is the condition for the existence of the differential resultant.
Is this related to your super essentiality?
Well, we will have to write how they are classified. No, this is different and is stronger. So is this differentially essential guarantees the existence of the differential resultant. Then you say which polynomials do really appear in the resultants.
That's right.
The ones who do really appear belong to a subsystem that they call rank essential, and this is more restricted than super essential. But rank essential implies super essential. So let's say if I demand super essential, what we can guarantee is that the order of the resultant is always less or equal than these Jacobi numbers. And if you but to guarantee that all of them appear, then you have to demand this rank essential that is strong.
In what sense is the word sparse here?
In what sense?
Does the word sparse here mean? I mean, when you define this abstractly, right, as a generator,
okay,
you don't know that the expression is actually sparse, except in the sense that you know, for a certain fixed order and degree, there are tons and tons of monomials, and of course it's sparse in that sense.
Right.
But you have no control of that. I mean, it could be really a fairly non-sparse one, right? In the end.
Mm-hmm. So generic non-sparse here means fixing order of the polynomials and degrees, all the monomials in there, whereas you say many of them.
Right.
Because you have. And then sparse means that maybe fixing the order, like we said, maybe one of the variables doesn't reach the order of the whole polynomial. Then we have order 3, the whole polynomial, but order 2 in one of the.
Differentiate so many times, and then in general the same.
In general, no, but yeah, that's one thing of that one case of sparse. The sparse here is what I was trying to motivate at the beginning, that it can be sparse because you don't reach the total order with all the variables, or it can be sparse because some monomials are missing.
Right. So if I take your given system and I homogenize it, in a sense I take a variable as a linear combination of all the variables and then substitute in the formula. Now then, if you start it that way, what would the effect be to the sparse resultant?
Let's see.
Because you see, if I start with the totally homogeneous one, so because it's totally non-sparse, right? You won't get the 0 columns probably, right? Because everything will be there.
No, you will.
You will.
That's the key here. That the starting one
Yeah.
will be non-sparse.
Right.
Every variable gets to the order. You have every monomial, but as soon as you derive, as an algebraic system, is sparse very often.
And also in the ordering.
So
when
let's
you
say
start
that.
using when you start doing the ordering of the variables in the algebraic sense, you do not require them to respect any differentiation. Right? I mean, you don't say that a high order one has to come before a low order one. You don't say that, right?
No, well, in principle not, but
you
this.
treat them equal in some sense.
Yeah, but I didn't mention that in the specialization, we do need to establish some condition for that, because otherwise, the specialization of the for these results about the resultant, differential resultant to be a factor and so on, we need to look at the intermediate. So we have the algebraic generic system, and we have to take subsystems and specializations of those, and that you will have to do it carefully.
Okay.
And for
Because
example,
in some sense, when you solve an algebraic system, I mean, because that's what you're doing. Right?
yes, in the end you do an
You're
algebraic
doing
system.
that, right? So you get a solution which is an algebraic solution to the system, but that need not be a differential solution.
Right. Yeah.
So we have to guarantee that in some sense.
Yeah. So it has some importance in this specialization in between.
All right. Any question? Now we thank Sonia again. We will recess to lunch until 1:30. Lunch is available up on the 8th floor.